All right, I literally just did this, and I didn't have the record button pressed, so I filled up the whole board, and then I had to erase the whole board, and now I'm starting over. So this is example 26.3 or 23.3, which we've done already, but I want to give you guys something to look back at if you have any questions, you want to go back and check it out again, make sure you kind of understand what's going on. So I'm going to go through it again with you guys just to make sure we're all confident. And I want to kind of go through it in terms of the electric field and the kind of model that we have for solving these problems, right? In the textbook, it's in a nice orange box, kind of emphasizes what kind of steps you should be taking. I forget what it looks like in the e-textbook, but I think it's pretty similar. So first step, right? We are trying to determine the field of charge, or the field of a line of charge. First step is to draw a picture and choose a coordinate system. So I have my line of charge there, but I'm going to draw a coordinate system on here. So I'm going to have the x-axis coming out this way. I'm going to have the y-axis this way, right? So my line of charge is on the x or the y-axis. My x-axis is coming out from the middle. So I draw a picture, establish a coordinate system. Step number 2, identify the point P at which you want to calculate the field. So I'm going to pick a point P out here. This is P. That's where I want to find the field. P. All right, that's where I want to find the field. Step number 3, divide the total charge Q, right? So this whole line of charge has a total charge of Q and a total length L, right? I'm going to break it up into tiny charges, right? And in this case, this is going to be delta Q, right? And it's going to have a length of delta Y, right? We're working on the y-axis, so that little section is going to have a length of delta Y. So I divided the total charge into a small piece of charge using shapes that I already know to determine E. So in this case, we're pretending that this little section is a point charge, right? And we know how to find the field of a point charge. It's KQ over R squared. So we've got that. Draw the electric field vector at P for one or two small pieces of charge. So step number 4, look here. The electric field at P from my charge Q is going to go this way, E. Now, we'll label this segment just for argument's sake, right? This is going to be segment I. We'll call it I for short. All right, so this is EI. All right, so that's the electric field from one of my segments. And then I want to kind of choose another segment and see what happens, see what it compares. Usually a good choice is directly opposite of the, or symmetrically opposite of what you're working with. So I'm going to draw the electric field for a tiny chest charge, delta Q down here. Also has a width, delta Y, right? But let's see. And what do we notice here, right? What's the point of that? What we should notice is that the Y component of the E field is canceling, right? So we're not going to have to worry about the Y component because every little segment of charge that I have there is going to have a component, or going to have an opposite on the other side of the x-axis. That's going to cancel with it. So our Y component of electric field is going to cancel. So we drew the electric field vector for one and two pieces. This helps us identify distances and angles. And step 5, look for symmetries of charge distribution that simplify the field, right? Which is what I just did there. We noticed that Y components are going to cancel between these two, which means I don't have to worry about Y components anymore. I can just focus on X components. I'm going to label 2 more things here, right? Theta I is this angle right here. and Ri is the distance from my segment I to the y-axis, or to the particle P. Okay, cool. So I got my problem set up now, right? That's the first step. Now I want to start actually solving for the field, right? And what I'm going to realize, right, is I have to figure out the x component of the electric field of I. So EI x, let's start with that, is going to equal our equation for a point charge, right, which is K 1 over 4 pi epsilon times Q, which in this case is my small delta Q, over Ri squared. Right, so that's my charge, but I'm picking out the x component, and if I look at my angle, theta I, x component is going to be a cosine, so cosine theta I. All right, cool. But I want to write this in terms of things that are on the coordinate system, right? So theta and r don't necessarily help me. Those are polar coordinates, and I don't necessarily want to work with polar coordinates right now. I want to work with Cartesians, right? So I'm going to take my values that I had that are kind of made up, right, that I just kind of made up for purpose of writing down the equation, and replace them with things that are legitimately on the x and y axis, so that if it comes to a point where I need to integrate along the x or integrate along the y, I have something that I can do that with. So Ri, right? Ri is the hypotenuse of this triangle right here. We'll call this distance r. So it's r to get from our axis to P. And then this distance right here, since we're on the y-axis, we'll call that yi, right? The height of that to get from the origin to my segment up there is yi. Not to be confused with delta y, right? Delta y is the width of this segment. Yi is how high above the axis or the origin my segment I is. So r squared, or Ri, is going to be r squared plus y squared, or yi squared, the square root of that. Since Ri is squared, we don't have to worry about the square root. So we'll rewrite this 1 over 4 pi epsilon delta Q over r squared, which is on the x-axis, which is good, right? That's something I can work with, plus yi squared, which is also good. That's on the y-axis. If it comes to integrating, I can do that. Cosine of theta, right? Our cosine is this angle right here, which matches with this angle. Cosine is going to be adjacent over hypotenuse. So r is adjacent over the hypotenuse is Ri, right? But we said we didn't want to use Ri because it's not on the x or y axis. So Ri we already solved for. Ri is the square root of, I guess I should write that somewhere. Ri is the square root of r squared plus yi squared. Right, so I'm going to put that in here. Square root of r squared plus yi squared. We can multiply these and we'll get 1 over 4 pi epsilon delta Q times r. Multiply these, that'll give us r squared plus yi squared to the 3 halves power. And there we have EI x, which looks very similar, and it should look very similar to the charge of a point charge, right? Which we solved for in, problem number, or example number 26.1, where that's what we were looking for, 26.2, I forget which one it was. Okay, so that's good, but it's not the endpoint, right? Because that only tells me the electric field from this individual segment, right? What I want is all of the segments on this circle, so I actually need to sum all of the EI x's, right? From I equals 1 to n, right? However many EI x's we choose to have. So that'll give us a summation I'm going to pull out the constants, 1 over 4 pi epsilon, because I don't need to worry about those in my summation. Sum from I equals 1 to n of delta q times r over 4 squared plus yi squared to the 3 halves. All right, so there's the summation that I'm working with. Now, again, not super specific, and we want to turn this into an integral, right? Because we want to take something over our full range here, and in order to do that, we're going to need to integrate. The problem here is I can't integrate over the value q, because delta q isn't a geometric, it's not a geometric, geometric concept? I don't know what the word I'm looking for. It's not geometric, right? Delta q is a charge. It's not geometric. We can't integrate over it. So we need to turn this into something that we can integrate over, right? Either x, right? We can integrate over length in the x. We can integrate over length in the y. In this case, we're going to integrate over length in the y. So we need to get this delta q out, and we need to replace it with a delta that we can integrate with. So how can we get rid of delta q? Well, we have this nice thing called charge density, which is equal to q over L, right? Charge density. And if I'm looking at this segment I, right, which has delta q, what's the length of this segment? Well, we said that was delta y, and delta y is something I can work with. So this is on a large scale. Lambda is q over L, right? Charge density is q over L. On a segment scale, lambda is equal to delta q over delta y, right? Our small length is not L, our small length is delta y. And now I can replace delta y, or I can replace delta q with lambda delta y. So we multiply it, right? Delta q is equal to lambda times delta y. And actually, we want to be as specific as possible here, so I don't really want a lambda in my equation either, because it's not a basic physics concept, right? Lambda is a little bit more complex. So I want to replace lambda with its original value, which is q over L. So my delta q is equal to q over L times delta y, right? We would replace the lambda with a large scale q over L. So if I come back over here, I'm going to replace delta q with q over L times delta y. So we get 1 over 4 pi epsilon. Oops. Summation I. We want to go to infinity, and instead of q, I'm going to have q over L delta y over, oh, I forgot the r. There's an r here too. Times r times delta y, right? There's an r right there. I almost forgot to write it. R squared plus yi squared to the 3 halves, right? And now we have something that we can take an infinite sum, which is an integral for, right? We can work with delta y there. So I can rewrite an integral here. I'm going to pull out all the constants so I don't have to worry about them in my integral. So 1 over 4 pi epsilon. I'm going to pull out the q r over L. Right, so qr over L, I'm going to pull it to the front because those are all constants in this case, which will leave me with the integral of delta y over r squared plus y squared to the 3 halves. And in this case, right, we have actual values that we can integrate over. We don't need an indefinite integral. We can take a definite integral. And we want the values to go from our low point here to our high point here. our low point here, because we split the rod in half, or the line of charge in half, is going to be negative L over 2, right? That would be the lowest that our Y value could be. Up here, it's going to be positive L over 2. That would be the highest that our YI value could be. So we're going to integrate from negative L over 2 to L over 2. Integral, very complicated. So I'm just going to give it to us. It's in the back of the book, in the appendix, if you want to go look for it. We end up with I think it's y over r squared plus y squared to the 1/2, if I recall correctly. Did I recall correctly? Y over y squared plus r squared. I missed something. What'd I miss? Q over L. R's on top. Let me go back to the appendix. I messed it up. What did I miss? What did I miss? What did I miss? It's appendix A. There's my integration. It's y over r squared. I forgot the r squared in the front. All right, there's an r squared in the front here. I forgot it. Now, because we have an r up top here and an r squared on the bottom here, this r will cancel and the square will cancel there. And now we've just got to plug in and work with what we've got. So this is from negative L over 2 to L over 2. I can pull the constant r out so that I don't have to worry about that. So we'll get Q over LR. And then here, when we plug in L over 2 and negative L over 2, we get L over 2 divided by R squared plus L over 2 squared to the 1/2 minus negative L over 2 over R squared plus negative L over 2 squared to the 1/2. And to simplify here, right, positive becomes positive, or negative becomes minus, and negative becomes plus and positive. Down here, because we're squaring that negative, that becomes positive, so we don't have to worry about that. Now they have the same denominator. We can combine them. L over 2 plus L over 2 is just L. So we end up with 1 over 4 pi epsilon naught Q over L R times L over the square root of R squared plus L over 2 squared. One last simplification, because there's an L on the top and the L on the bottom, we can cancel that and cancel that. And we end up with a final answer. The electric field from a line of charge, call it LOC, is equal to 1 over 4 pi epsilon naught Q over R square root R squared plus L over 2 squared. And that is our value for the electric field of a line of charge. Double check just to make sure I got it right. 1 over 4 pi epsilon naught times Q over R times R squared plus L over 2 squared, square rooted. Excellent. Hopefully I recorded it this time. I did.